Ocean, we said many times, takes up more than 90% of the excess energy that human beings are trapping by increasing greenhouse gases. Can we get the ocean to do more for us? It takes up 25% of the carbon emissions. So obviously humans are contributing to increasing the CO2. Just like we had detection and attribution, for dealing with climate change, we have two things, adaptation and mitigation. Adaptation is where we say the change is inevitable or is already happening, and we try to live with it, and we make different rules to deal with it. For extreme rain, how to deal with extreme rain, droughts, agricultural practices, building codes, etc. Right? And then there is mitigation, which is to reduce our impact on the climate, let's say by either taking down carbon dioxide that we have already emitted or we will emit, or renewable energy sources. So it's essentially reducing our global warming potential in the first place. Okay, adaptation, mitigation. So these mitigation efforts are broadly considered geoengineering or global engineering attempts to counteract human-caused climate change, and they include many ideas like reducing the sunlight reaching the earth itself. We can use the analogy of volcanoes, for example. When big volcanoes go off, they can put so much dust and ash in the stratosphere that can stay for several years and produce a net cooling. Remember the year without summer because of the Indonesian volcanic eruption, Edvard Munch's The Scream painting, crop failures in England because of this year without summer, and so on. So it's not all hunky-dory, because if you put ash, eventually it'll fall down. Stratosphere has very little weather. Remember, it has a warming profile compared to the tropospheric profile. There's not much weather in the stratosphere. So things that go into the stratosphere have a longer residence time. They can stay there for longer, but eventually they have to come down. So you could end up with acid rain, etc. But the more important thing is that even if you block out the sunlight and reduce the warming, the CO2 still has to be taken care of. It's still sitting there, it's still doing acidification, it's still doing all the bad things on health, etc. So it's not a real solution in that sense. Removing human-caused greenhouse gases, so-called carbon capture and sequestration. Can we use natural cycles to do that? There is some evidence that there is something called carbon fertilization, which means as you increase carbon dioxide, photosynthesizers are able to grow faster. It's like a fertilizer, and they are able to sequester more carbon. Okay, so carbon fertilization is one thing. In the ocean, we talked about the biological pump, which takes out CO2, so we have low CO2 near the surface, right? And it's a sink of carbon dioxide, especially if the material that's photosynthesized, the carbohydrates, can sink to the bottom, because then they get buried and become part of the geologic cycle over time. Things like lime rocks and Dover Cliff in England, which is all calcium carbonate, are produced by these biological activities and the carbon biological pump that put the material away. Okay, so the reactions, of course, here 6H2 CO2 plus 6H2O giving you carbohydrate and oxygen. Respiration would return it back into CO2, but there is sedimentation, so carbon dioxide and nutrients from the upper ocean are being dropped into the ocean. So unlike land, ocean has this depth that it can use for various effects, right? So can we somehow accelerate this photosynthetic activity and make more CO2 go into the atmosphere, into the ocean? Okay, so we have already seen the ocean's role as a thermal sponge, right? We looked at the contributions from surface to 2300 feet. We keep switching the units, but never mind. And the deeper ocean from 2300 to 6560 feet, and then very deep ocean below 6 kilometers. Very deep ocean. Very few parts of the ocean are that deep anyways. So ocean is taking up all this energy, but what about the potential for increasing photosynthesis? Remember, we said there are some places like the Eastern Pacific where there is upwelling, lots of nutrients coming up, but still all the nutrients are not used up. All the nitrate, for example, is not used up because not enough iron is available. So as human beings, we need multivitamins, right? We need iron, zinc, calcium, vitamin D3, vitamin K, this and that. Just the same way life in the ocean, photosynthesizers need macronutrients like nitrate, but also micronutrients like iron. And if there is not enough iron in the water, then the nutrients nitrate doesn't get used up, and those are called high nitrate, low chlorophyll regions, or HNLC regions. Okay, high nitrate, low chlorophyll regions. And the idea is that because these are iron deficient, can we go in a ship and dump a bunch of powdered iron that can dissolve in the water and accelerate photosynthesis? This is called ocean fertilization or iron fertilization. So Southern Ocean is another region where we know that there is a iron limitation for photosynthesis. A lot of nitrate can come up, but it may not be fully utilized because not enough iron is available. There are places where phosphorus is limiting and so on. So people have tried this. They have gone in the Eastern Pacific, they have gone in the Southern Ocean, they have dumped iron overboard from a ship, and they have measured for several weeks how photosynthesis responds. It turns out that photosynthesis does go up, but what has to happen? If you want CO2 to go down to the bottom, you have to have photosynthesized material sink to the bottom, and that happens with certain species of phytoplankton, like diatoms are heavier, they are better at exporting. There are other details that even smaller phytoplankton can cluster together and sink to the bottom, etc. But the net story is that it turned out when you go and dump iron, lots of recycling happens near the surface and very little export gets enhanced. Export doesn't get enhanced much, so there is no effective excess drawdown of CO2 because of iron fertilization. But also remember eutrophication. What happens when you have excess nutrients and excess recycling? The aerobic respirers use up that carbohydrate produced by this iron fertilization, and they utilize more oxygen. So you are actually going to create an oxygen problem for other heterotrophs who are used to living there. Okay, so right now the scientific consensus is that iron fertilization is not good. It doesn't work, and it has in fact been banned. No private company can go and take money from people and saying, I will reduce your carbon footprint if you give me money, and I'll go and dump iron in the ocean and take down the carbon dioxide that you're emitting from your industry or from your vehicles or whatever. Okay, so good idea, but doesn't work. Hypothetically good idea, but doesn't work. In the atmosphere, there are other ideas for going in an airplane and sprinkling dust, putting mirrors to reflect sunlight and so on. But as I said, they do not remove the CO2. CO2 is still a problem. So reducing warming is one thing, but reducing CO2 is another thing. So carbon capture and sequestration is a big science research agenda. Taking out CO2, which is only 0.04% in the atmosphere, is not easy. Taking it down at sources where they are produced, like power plants, is being tried, is being done, but how much does it cost to take down that energy? How will you manage the energy usage? Right? So there has to be a scale, there has to be an efficiency, there has to be return on investments, or the government has to subsidize it. So whole geoengineering is a very active field of research. It will be done in some form or the other, but right now we don't have scalable systems to remove enough carbon dioxide.